All right, this is our second lecture now, Tuesdays. Last time we talked about sequences, so I remind you a sequence that was just basically a list of numbers. And I'm going to give you one example because we're going to work a little bit with this one. And then what normally comes when you write this down, you write dot 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 because it goes on forever. A sequence is an infinite list of numbers. And the idea is that this dot 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 means that we kind of can figure out what is the next one in the sequence. And of course, in this case, I guess everybody hopefully sees this, that it would be 1 over 32. Because what we have here in the bottom are actually powers of 2. Right? So we could actually even decide what the formula would be for such a sequence. Right? In general, we have a sequence, then we call this A1 and this A2. And then A3. Now this is if we start from 1. Sometimes we start from 0 or from some other number. It's just a choice that we make that fits best the actual sequence that we're looking at. And we have seen that most of these sequences have a formula. But again, about the formulas, how to find these formulas, that's not going to be a problem. We're always going to have a formula. So let me tell you what the formula is, and you can verify that this is indeed a formula. An here is 1/2 to the n. Right? The denominators, the numerators are always 1, and denominators are the successive powers of 2. I hope this is now clear for everyone. And in fact, you see here that you get from one number to the other. So go from there to there, for instance, is by multiplying with 1/2. So this is something that we call a geometric series, or geometric sequence, sorry. We are not talking about sequences yet. So a geometric sequence. And then we say that this factor that we use here, that we call 1/2. Now I'll come back to this geometric sequence, don't worry about it, but just pointing out already that this is an example of it. Now this is not a topic. What is series now? Well, a series is now, what we do is when we have this a sequence like that, we build a series. Basically, what we do is we take all the numbers in the list and start adding them up. 1/2 plus 1/4 plus 1/8 plus 1/16. The next one we know already was 32, and then you can fill in again dot dot dot. So the only difference is if you want, instead of these commas now that separate them, we have actually all these additions that we have. Okay. But you will say, what on earth does it mean? Okay, I know what to do with 5 or 6 or 10 or 20 numbers, but what infinitely many, what does that mean? Does that even make sense? Is that even possible? Look, you say, let me do, before I go on this one, let's take a series that obviously never is going to work. Take a series that is always 1. So 1, 1, 1, 1, 1. So that means the general formula would be just 1, right? So this is a new example. This would be the series 1, the sequence 1, 1, 1, 1, 1. Now if you make the series of that, so the series that you would get would be 1 plus 1 plus 1 plus 1 plus 1, and so on. Now this gets bigger and bigger. The more you add, the bigger it becomes. So it's no surprise that we'll say this is infinite. Or the right terminology is something that we already heard of, is this is divergent. There's no way that you can add all these numbers. Okay, you say this is going to always be the case. If I add quantities, no matter how small, they're going to all add up. It's too many, it's infinitely many. How can that ever work? Well, this is actually what the rest of the course, the sections, this chapter will be about, is showing that actually in many cases it can actually work. And the answer, in other words, the answer is not infinity. The answer is therefore what we call the opposite of divergent, convergent. And this is the series that I wrote down here. This one is an example of such a thing. Now, before I go into the theory of this a little bit, I will see formulas that actually will calculate this in a sec. But for now, I just want to give you a visual proof that this works. Okay, so what I do here, I'm going to look at the line. So this is, here is 0 and here is 1. And let's play a game. And I say I start at 0. This is my starting position here. And my goal is to reach there. And what I'm allowed to do at each step of this game, I'm allowed to go cut my distance in half to where I need to be. So this is my target here. So let's say there's something very desirable here, whatever you desire the most. Let's make it a cake. Okay, and so we're all trying to get to this cake, and at each time you can halve your distance to this cake. Okay, so the first time I do this, where will I end up? Halfway, right? So I will end up here. This is the point a half. Okay, so what's the distance I traveled? I'll make a different color, telling me this distance that I traveled is a half. Okay, I will play the game next time. We can do it again. Now I'm going to halve my distance between, I'm here now, right? So I'm trying to get there. So what is my distance now? Well, I can go half, half, a half. So this is, let's see, we can go 1/4, right? This puts me here. This is 1/4. And so where does it put me? Well, it's not hard to see that we get here at 3/4, right? In fact, what it is a half plus a fourth. That's exactly 3/4. Okay. Keep doing this. If I go another halfway, I will end up here. Everybody sees what it is. Try to calculate it. It is 7/8, and the distance that I traveled is now half the previous distance. So this would be 1/8. You see, these are exactly the numbers, half, 1/4, 1/8, that we had in our series. And the total distance here, this thing here, is exactly the sum of these three numbers here, right? And so the more I go, more of these elements that I look through this sum here, corresponds to me moving closer and closer to my goal. But you see, I'll never get there, right? In any finite steps, there's always some distance left. And I do it again. I go half. Let's do it one more time. If I go halfway, I will be here. Oh, this is the wrong color. I will be here. And this would be at, anybody guess? 15/16. Why? Because this distance is 1/16. It's half the distance of the previous one. The previous one was 1/8, now it's 1/16. And if you add 7/8 and another 1/16, you get 15/16. Okay. And so this time I would have now these four guys, if you look at the total distance now. And what you see is that actually I never, at any finite stage, I never get to my goal. So in other words, at any stage, the sum of all these numbers that I'm adding up will never be bigger than 1. So this already tells you you're not ending up in infinity. You're going to actually end up less than 1, or perhaps equal to 1. Well, at any finite state, you will be less than 1, and this is now the beauty of it. In the limit, you will actually be at 1. I hope that is kind of clear. If you imagine this always getting closer and closer, at the end, you have to have a magnifying glass to see even the difference, and at infinite many steps in the limit, we will actually be there. Okay. But that is just a picture. So now how does it work officially? What's the official definition of this thing? So let me go back to a more general situation, and we'll go back to our example. We have a sequence, and we said this is given, we number them an, and n goes from 1, 2, 3, or sometimes from 0, 1, 2, 3. And normally an is given by a formula. And then to this sequence we add the series, and here is the notation. So what we do is, perhaps it's better to, no, sorry, that's not what I want to do. What I want to do is this here. Let me perhaps list the sequence here. We have A1, A2, A3, A4, dot, dot, dot. So we started from 1. Now what's the series is going to be that I'm actually going to add these elements, right? That's what I said it's going to be. And here's this notation for it. This symbol is it's called a capital sigma. So this is sigma, the capital Greek letter sigma, and sigma is the Greek letter for S, and this stands for S of sum. And so this is the sum of the AN. So that is what we mean by this. And now to make it clear that what we are adding is, we say, okay, our index starts from 1, because that's where we start for, and we go all the way to infinity. Okay? Because this dot 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 means that we go on forever. That's why we have infinity on the top here. Okay. You can think of this as perhaps similar like if you're doing computer programming for a for loop, for n going from 1 to, and sometimes in computer science we use this symbol sigma. The sigma symbol is used as 2, but then instead of infinity one has a finite step, of course. Computer program has to end at some point. But we are now dealing with infinite sums, so a series, we have infinity. In other words, another way of saying this, what it means is that a series is really just an infinite sum. So that's an infinite sum. That's what a series is. Now, how do you make sense of this? Okay. So what we did here in the previous case, what we actually were calculating, if we looked at these various numbers here, these positions that we found, these were the result of actually adding up the first few, right? This one was just the first one. This number corresponded to adding up these two. This number corresponding up to all three of them, and then this one was all four of them, and so on. So these were sums, but not the full sums, but what we call partial sums. So that's a very important concept. So we have the partial sum, partial sums. And we're going to use a little s for that, s of n. So S1 is just going to be the sum of the first one, that's A1. S2 is the sum of the first two, A1 plus A2. This is S2. Okay. And S3, we keep going, A1 plus A2 plus A3, so this will be S3. Okay, and so on. So, and so on. What does it mean? I'm actually generating a new sequence. Notice it's not the original one, this is the ANs, but now I get the partial sums. These are going to be the SNs. Okay, and now comes the definition. We say that the sum of this series, AN, is the limit of these SNs. Right? Look at what we did here. The partial sums, I remind you, these were the SNs here. These were listed here in the bottom. Right? This for instance was S4. And on top here, the orange numbers, these were the ANs, right? A half, 1/4, 1/8. These were the numbers inside my series. Okay, so we have now a new sequence, the SNs, and look what is the limit of this sequence. Well, visually we see that these numbers will get closer and closer to 1 here, but we can actually even verify this. So let's try to do this. So first, that means we need a formula for SN. As I said, this is not something we should worry too much about, but in this particular, I'm just going to give the example now, work it out. But this is not something you're supposed to be doing on your own. So let's work out the example ourselves here. But it's actually not so hard in this case, because if you look at the shape of the SNs here, you see that the denominators are again powers of 2, right? Powers of 2 here. And the numerators, well, what's the relationship between the numerator, this guy and this guy? Just one less, the top one, right? So, okay, so let's see, what does this mean? So we go back to our example. So this is the example, let me go here, oh no, let me do it in black. What is going on here? Example that we were doing a half plus 1/4 plus 1/8 plus so I'm just saying this is what we go. So let's calculate what S1 so we had them, right? This was a half, S2 was 3/4, S3 was 7/8, right? In case you don't believe me, and so on. So what we see is that there's the pattern is very easy. The denominator is again the same power of 2 to the n, right? The ANs, remember the formula for that was this. And now this is the ANs here, but you see this is A3 and the corresponding S3, this is S3, this is A3, right? If I just list everything, you see the corresponding denominators are the same. And what we said was that the numerator is just one less, so let's just subtract 1 from it. Okay, and so what we have to do, according to the definition now, the definition says you have to calculate the limit of this guy, 2 to the n minus 1 over 2 to the n. If I plug in infinity, that's an exponential function divided by, both are infinite, right? So we have to do this in indeterminate form, we need to do something, okay? We can use there are many things you can do here. I'm going to use the most straightforward one, is what you all kind of like to do, is the L'Hopital here. To do that, I should kind of write it as a function, not in n, but as a real function in a variable x. So I'm just doing that for making everything look correct. Other people are going to watch this movie and they say, hey, what are you doing? So I have to make sure that I do everything correct here. This is a function now, a continuous function of which I calculate the limit, and that I can use the L'Hopital's rule for. And that means that what I'm going to do is, I'll write it down here, that I have to take the derivative of the top. Now, derivative of the exponential function is the exponential function times the logarithm of the base. And then just minus 1, of course, that's nothing, right? The derivative of that is 0. And therefore, the derivative of the bottom is the same thing, 2x ln 2. So this, everything cancels out here. This is important, of course. Every time you do L'Hopital, you have to see whether there is any cancellations possible. And be careful. The original one, you might be tempted to say, look, let's do something wrong. Say, oh, I see, this cancels with that. No, no, no. You cannot cancel within a sum. This is a total sum here. So if you do this, what the correct way to do is divide each term by 2 to the n. So this would be 1 minus 1 to the n, and not just minus 1. You see the difference? Okay, but let's go back to what we were doing. Let me erase this so not to confuse you. Okay, so as I said, we cancel everything and we see that it's just 1, right? There's nothing, there's no limit left anymore. And that's exactly what we said it would be, right? We were guessing here that this sum here would be equal to 1. That's what we would get here. And now we've seen the proof of that, so we can now say that this is a series that is convergent. Remember, this refers to the fact that the limit actually exists. It's a number, so this is convergent, and it's equal to 1 here. Now, this is something, a little bit of a bonus, if you want, that we know what the answer is. And this is going to be a bit strange in this topic, is that we very often will be able to say convergent, that we will be able to say, but what's the actual value? That's going to be much harder. And that is actually often problems for higher courses, level courses, so we won't even address this. But this is a case where we do have an example where it works. Now, we have already seen where it blows up. Let's just look at this one here, this example. We said this is not possible. Well, let's calculate what the S1 is, this partial sum zone. Well, if you add the first element, you get 1. If you add the first 2 elements, you get 2. If you add the first 3 elements, you get 3, obviously, right? So, what is Sn? Same as its index, right? So it's just n. And what's the limit? The limit for n going to infinity of n, well, that's infinity. So that's why we got this conclusion of a divergent sequence. Okay? I want to give you one to show you that you have to be a bit careful with this notion, and it's very important to do that this is the correct definition. And so here is an example of another series now. So the sequence, we talked about this sequence already, so let me repeat it. The alternating sequence. This was just pluses and minus ones. 1, and then minus 1, 1, minus 1, 1, minus 1, dot, dot, dot. Okay, and the formula, by the way, not that we're going to really use it, is minus 1 to the power. Well, now it depends. Where am I starting from? So I'm gonna, to make life easy, I'm gonna call this A0. So I start from 0, and this A1. Why do I do this? Sorry, no, I don't mean to say this. So this is A1, and this would be A2. Why do I choose to start from 0? Because then the even indices correspond to the even powers of -1. So I can use this as my formula. If I would start from 1, I have to adjust this by, instead of n, I have to write n minus 1. But let's not dwell too much on that. Let's look at the series. So what do we get if I do the series here? I get 1 plus minus 1 plus 1 plus minus 1 plus 1 plus minus 1 plus the dot. Oh, I see the value. You say, look, it's easy, right? These two are equal to 0. These two cancel out to 0. These two cancel out to 0. So this goes on. The whole thing is equal to 0. There you are. Okay, okay, right? But can I do something else? Like, look, I'm going to do it slightly different. I agree with you. These two are equal to 0, right? Minus 1 plus 1 is 0. Now, if I group these two together, that's equal to 0. I agree with you. And here, the next one would be a 1. So if I group these together, is 0. So if I go on, everything is 0, except for the first one, because that's a 1. So the whole thing is equal to 1. Yeah, wait. That's not possible. I cannot get two different answers. The green answer is 0 and the purple answer is 1. Which one is correct? Well, normally in this kind of case means none of them is correct. Why is that? Well, let's go back to our actual definition. The definition was we have to actually work with the partial sums. So let's write those down. S1, the sum of the first element, that was just, or in this case, sorry, S1, no, we can start from 0, so I should not call it S1, I should call it S0, right? So let's, S0 is 1, S1, the sum of the first two, that was exactly what this green calculation did, was 0. What is S3? Sorry, S2. So now we have to sum up these three guys. Sorry, I'm going too far. These three guys here. And if I add them up, 1 plus minus 1 plus 1, I get 1. And S3, not hard to see, right? Now I'm adding up all these four here, and I get 0. And it's clear what the pattern is going to be, right? We're going to get alternating 1s and 0s, so on. And remember this sequence, or a similar sequence we saw, it's a sequence that keeps jumping from one value to the other. So the limit of this sequence does not exist. So this is the limit here, that's what I mean with this arrow, does not exist. It's not infinity, it's not 0, because if it's 0, that means from some point onwards I have to be very close to 0, always. But I'm not, because if I have an even index, you see my partial sums are 1, that's far away from 0. Okay? So this is an example where the limit does not even exist, and therefore we will say that this is again a divergent series. And that explains the reason why we get two different answers if we try to just guess what the answer is. Okay, so that's about the general theory of limits. Now in the book they discuss quite a lot of that, and somehow I'm not going to be interested in most of the problems in the book, and you'll see I'll adjust the homework problems as well. Because whatever is discussed in this particular section, we will later on discuss again in more detail when we have better techniques. So it's better to wait until we have the right techniques. Okay, so therefore what I want to do is I'm going to skip therefore most of the topics here that is covered and go to the one very important case that is going to be something that we're going to work with a lot, and this is the so-called, well, we have seen it already, I told you I'm going to talk about it, it's the geometric series. So I remind you again what a geometric series is, and to do that, let me just put an example. Look at this series here. Let's see, which one would I take? Sorry, let me give me 1 sec here, I want to get one. Okay, this one. 4, 2, 1, 1, 4. This is a very simple one. 1, 8, dot, dot, dot. So this is what I call, of course this is not a series, this is a sequence, right? So this is a geometric sequence. Now, how do we know this? Well, because there is a fixed ratio, so there's an R, that if I multiply any element with that R, I get the next element. That's the recipe. And it must work for everything, otherwise it's not a geometric sequence. And everybody sees it here, R is a half again. Remember the original sequence that I've discussed, I told you it was a geometric sequence also with a half. Okay, but that doesn't have to be a half, we'll do another one later. Okay. So, in general, let's just write down a little bit more generally how it looks like. In general, a geometric sequence, and it's easier now again to start from 0. That we have a 0, A1, A2, A3, and so on. So A0, okay, we start with something. You see here we started with 4. And we're going to give a special letter to this because we're going to use this in the formula. We call A the first one. So a geometric sequence is determined by two things only. We need to know what the R is, and we know where to start. Because once we know where to start, we know how to get the next one. Namely, take this number and multiply it with that, and you get the next one, and so on and so on. Okay, so A0, that is just A. What is then A1? Well, as I said, you take A and multiply it with R. So this is AR. And what is A2 then? Well, you take this guy, A1, and multiply it with R. So what do you get? AR squared, right? And then how do you get to A3? Well, you go look at the previous one and multiply with R. And then you get this one. So this is AR squared times R, that's AR cubed. So we see that we actually get a formula here. AN is AR to the power N. And that's because I started from 0. That's why in the textbook they start from 1. I don't know why, I find it confusing. It's easier to start from 0. And so this is geometric sequence. The question is now, what's the geometric series? Which is the same thing, except that instead of listing them, we're going to add them all them. So the question is, what is summation n going from 0, because I started 0, to infinity, an, so this would be the summation ar to the n. I'm just using the formula here. Which means, just write out what it means, it would be a plus ar squared plus... So very often, instead of using the sigma symbol, we just write down the very first few terms. I'm very happy, in most cases, I'm okay with you doing it that way. Okay, so what is this now? Well, I'm not going to give this in general, but I'm going to give you the answer right away. If this is a geometric sequence, there are two possibilities. Either the r, the absolute value of r is less than 1, and then the sequence is convergent to the form given, this is wrong. It's equal to a divided by 1 minus r. And so this is the case of convergence. And what is the divergent case? Well, everything else. That means if the absolute value of r is bigger or equal to 1, say even equal to 1, then we have divergence. And of course, then if it's divergent, there's no point in saying something, it's divergent, right? You cannot add up these elements, meaning to say they blow up in your face, they get way too big. So in the case here of this sequence here, so let's make it a series now by putting pluses here. So what is this now? Well, now it's easy, right? This is equal to, well, first of all, let's look at r. R is positive, so there's no absolute value here. Is it, in which direction we are? We are in the conversion part, right? R is less than a half. Less than 1. A half is less than 1, sorry, I said misformulated. Okay, so we can use the formula. What is a here? Well, a is 4. So the formula is 4 divided by 1 minus a half. 1 minus r. This is the formula. Okay? And so I can simplify this as 4 divided by a half, and then dividing by a fraction is multiplying by the reciprocal, so 4 times 2 over 1, which is 8. There you have it. Okay, let's do another one. Let's take a slightly more difficult thing. Let's take 9 halves and then minus 3, sorry, that's what I mean. And then the next one is going to be 1, no, it's going to be 2, and okay, give me a second, I have to make sure that I don't make a mistake. Okay, and then the next one will be minus 4/3, and then the next one, I'll do one more for you, 8/9, and so on. I'm claiming this is a geometric sequence. Of course, it's much harder to see, right, if it's fractions like that this is a geometric sequence. So you have to trust me, this is a geometric sequence, and if it's a geometric sequence, then at least we can find out what a and r is. Well, a is the easiest one, that's just the first element. There's no, you don't have to think about that, it's always that. What is r here? Well, r is what we need to multiply an element with, let's say this one, to get that one. So that's going to be r, multiply with r. Another way of saying that is, it's the same thing as, so the same would be to go from here to there multiplied by r. Or you can say it the other way around. What does this mean? So let's see. Let's call this r here. Minus 3 times r, that should give me 2. And now I can solve for r, right? This is what that needs to be done. If I go from there to there, that means, if I go from there to there, that means I have to take minus 3 and multiply it with r to get 2. So we solve for this and we see that r is minus 2/3. So once you have a geometric, if you know it's a geometric sequence, so that's, I'm telling you this is a geometric sequence, trust me. But once you know it, it's very easy to find what r is. You just take any two numbers and you take the quotient of the next one divided by the previous one. So if you take, for instance, if you don't trust me that this is correct, let's take this one. So as I said, you take this number, 8, 9, and divide it by the previous one, minus 4/3. That is 8 over 9 times the reciprocal, 3 over 4. There's a minus sign here. Well, and then you have a lot of cancellations. There's a 2 here and the 3 left, so I get minus 2/3. Okay, again, the same r that I was stating. This should always be the same. Okay, so we know what r is. So let me erase this now a little bit and just write down what we have. So we know that r is minus 2/3. And again, don't worry about, most of the time you will actually get this. They will tell you this is r. Okay, so don't worry too much about that. And now, well, where are we? Are we in convergent or divergent? I hope everybody sees that we are, if the absolute value of r, that is 2/3, which is still less than 1, therefore we are convergent, and we have the formula. So we know now if we, instead of commas, we put pluses, so we make it into a series now, then this plus dot 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 is equal to, and so I'm going to write it here, a over 1 minus r, that is 9/2 divided by 1 minus r. Be careful, here in the formula it's r itself. To check, you need the absolute value, but when you plug in, you have to plug in r itself. So this would be minus 2/3 here. Don't forget the minus sign. So we get 9/2 divided by 1 plus 2/3, which is 5/3. So this is 9/2 divided by 5/3. That would be equal to 9/2 times 3/5. Wait, did I do that correctly? For some reason I feel that I did something wrong, but it's right, right? Plus 2/3, 5/3. Yep. So that would be 27 over 10. Okay. And so just be careful. I'll do one more that you have to show you that some care has to be taken. So let's take this one here. We have 10 plus minus 5 over 2. No, sorry, that's not what I want to do. Sorry. Plus minus 25 plus 125 over 2 plus minus 625 over 4 and so on. Let's see what we have here. Again, I'm claiming, so this is something that you have to just take on faith, that this is a geometric series. And so we can now write down what A is, and the main question is what is R. And as I said, if it's a geometric series, then take any, to calculate R here, for instance, from here to there, you see that 10R is equal to minus 25. And so I can solve for R, and I see that R is minus 25 divided by 10, which is minus 5/2. Okay, and just checking now this works. If I multiply this with minus 5 over 2, I get exactly this number, and so on. Okay. So this is less than 1, right? Because it's a negative number. So this means it's convergent. Oh, wait. We said it has to be the absolute value here. So let's look at the absolute value of r. That is 5/2, which is bigger than 1. And therefore, this is divergent. No need to go to this formula. Of course, you can plug it in and you get a value, but it doesn't mean anything. It only means something when your r is less than, in absolute value, less than 1. Otherwise, it's divergent. It means that these numbers actually don't add up to something finite. They blow up. Okay? That's and now I want to finish with one application, a very interesting application. And this actually goes back to something you learned probably already in, I don't know, grade school, when they talked about decimal numbers. Let's look. So here is a decimal number here. What does this mean with this bar on top of that? It means that we repeat this. This is a periodic decimal. So the actual meaning of that is you take this 2, 3 and you keep adding it. These are always repeated decimals. Okay? And then they told you that this is always a fraction. These fractions are always for this form. Now we know this, for instance, if I take 1/3, if I do this in a calculator, I get 0, 0, 3, 3, 3, and so on, right? So, right. That is, if I can write it this way. So fractions are of this form, and actually the opposite they told you, or perhaps they even didn't tell you that, also true. But they never told you how, if this is a fraction, which fraction is it, right? How can I know which fraction this is? And that's what I'm going to do now today. All right. Using geometric series. Okay, so here we go. I'll work it out on the example that we have. Well, we have a repetitive part and a non-repetitive part, and it's important that we split them. So let's look at the repetitive part here. This is the bit that keeps repeating itself. Okay, and this is something I'm going to deal with later. So I'll pause a little bit, and I'm going to now work only with the part that repeats itself, because that is actually the geometric sequence. Why is that? Well, what does it mean? Right. Let's write down what it means. It means this thing, right? And you keep writing 2, 3, 3, 3. So let's break it down in parts. This is 0.023. I'm looking at this plus 0.3023 plus 0.234523 plus, and so on. Are you following this? Right? If I would add up all these numbers here, I do get this one. You agree with me? Okay. Now my claim is that this actually is a geometric series. Well, it's easier to write it as fractions, so let's write it as fractions. This is 23 over 1/10 100,000 over 1,000, right? Plus, what is this? Well, it's 10 100,000, 10,000, 100,000, so 23 100,000. The next one is, I'll let you think about it, it's actually 10 million. Plus. And this is, why is this a geometric series? Well, because there's a factor here that I can multiply this with. And what is this factor? Well, you don't do anything with the tops, right? That's always multiplying with 1, so the top is going to be 1. And what do I multiply in the bottom with? Well, from 1,000 I go to 100,000. From 100,000 I go to 10 million. That means I multiply each time with 100. Okay? And that, of course, is less than 1. So we are in the case, and this is always going to be, we're always in this case here. And now, therefore, we can use this formula. Let me write the formula over again. So we know that this is equal to A over 1 minus R. What is A here? Well, that was the easy part. That's always the first one. So we get 23 over 1,000 divided by 1 minus 1 over 100. And there are two ways of doing it. You can put it on common denominators and flip over. My preferred way of solving this is multiplying top and bottom with the common denominator. So in this case, I hope you see this, that 1,000 is the biggest common denominator here. So let me make me a little bit space here. I'm going to erase this a little bit. That if I multiply this with 1,000 and I multiply this with 1,000, then I will get rid of all the denominators. Okay. In the top, of course, I get simply 23, and in the bottom, if I multiply this 1,000, of course I have to distribute it, so I get 1,000 minus 1000 divided by 100 is 10. And so I get 23 over 990. Granted, you can also do this a different way. You can put this on the denominator and common denominator and work it out. You will get the same thing. Do that for yourself if you don't believe it. Now, we have to be careful because actually I only did this one, right? So what I'm saying is that this part is 23 over 990. But what about this guy? Well, it's also a fraction. If I want to get rid of the decimal, what we do is we move the decimal and we divide by 10, right? So we get that this is equal to that. And again, I can put this on common denominator. This time I have to multiply this with 99. That's going to be my common denominator, right? 990. I hope you see this, okay? And so the question now is, okay, 21 times 99. Let's work it out with the calculator. That happens to be 2079. We have the 23 here, and in the bottom we have 990. So if I put this on a common, work it out, I get 12, okay, and then 0, 1, 2 over 990. And this is now easy. You can easily check this by actually working out this fraction on a calculator. And, oh, I made a mistake. What did I do wrong? No, I added up. No, 12, 9, 10. Wait, I somehow seem to have missed 21 times 99, 2079 plus 23. Okay. Oh no, I just punched in the wrong numbers. Okay, it is correct. Okay. We get exactly the number that I had write down. And see, even if you make the slightest mistake, even if you write a 1 instead of a 2 there, the number will come out completely different, with a totally different pattern. So it's very easy to check your answer on this one once you've done it. But on a test, again, you have to show all the steps. You have to show me how you get from this number to there. Using intermediate step. There are different methods, by the way. Some of you might know it, but it's fine. But you have to show all the steps in the calculation. Okay? All right. So on the homework problems, I will give you some of these because I don't think they are in the text. The textbook describes this also, this method of decimal repetitive fractions, but there's no homework problem. So I will assign homework problems on that, and then next time we'll start with our tests. So that's what the rest of this chapter will be about, is about various tests for convergences. Okay, so we have, this is an example of a test, namely the test here is that it all just depends on R, whether a geometric series is convergent or not. But many series are not geometric series, so and the test will be much more complicated. Okay.